Okay, so we are trying some new software. So we're going to see how this goes. In this video, we are talking about topic 1.5, so atomic structure and electron configuration. So ultimately, we need to be able to represent the electron configuration of an element or ions of an element using the Aufbau principle. So let's review some atomic structure. So as you already know, we have three subatomic particles. We have protons and neutrons, and those make up our nucleus. Your protons are positively charged, your neutrons are neutral. Your electrons live in energy levels around the nucleus. So they live in energy levels like layers of an onion. And the electrons are negatively charged. So in a neutral atom, you have equal numbers of protons and electrons. Protons and neutrons contribute to the mass, electrons do not. Neutrons don't contribute to the charge. So that is what we know from our previous chemistry classes. Now we're going to introduce something new called Coulombs Law, and we're going to use Coulombs Law to explain a lot of different things. Okay, and so Coulombs Law mathematically says the Coulombic force, so it's a force, is proportional to the two charges multiplied by each other and then divided by the distance between them squared. So we use this to calculate the force between two charged particles. You're never going to have to actually be able to calculate anything, but you should have a good qualitative sense of Coulomb's law. So if you have a stronger attraction between the electrons and protons, so that's going to happen when they're closer together or when there's more of them, because you're dividing by the distance. So the greater the distance, the lower the force. The greater your charge, the higher the force. And then there's going to be repulsion between electrons because they're the same charge, and between protons because they're the same charge. So like things repel and opposites attract. And then we're going to use this to kind of give a quantitative sense to what that attraction or repulsion is. However, we're never actually going to have to calculate it. So just some terminology. So your electrons, again, they live in energy levels, so those are on the outside of your atom. The inner electrons are considered the core electrons. The outside electrons are considered the valence electrons. So we've used that term before. We might not have used core before. But your outermost energy level that's occupied is your valence energy level, and those are your valence electrons. Anything else are considered core electrons. So they're either valence or core. They're one or the other. And as you add energy levels, your valence electrons become your core electrons as you add more electrons. And the ones that actually do anything in terms of bonding are the valence electrons. So I like to refer to them as the business electrons, because those are the ones that are actually doing any of the work of an atom. One of the things we talk about with these electrons is something called ionization energy. That's the amount of energy you need to remove an electron from an atom, and it's related to Coulomb's law. So the stronger the attraction, the more energy it requires to remove the electron. So if you think about magnets, magnets are a really good model for this. If you have really strong magnets, it's going to take a lot of energy, a lot of force from you to be able to pull them apart. If they're repelling each other, electrons or magnets, then there's going to be less energy needed to remove. Okay, so the stronger they're being held, the more energy you need to remove them. Effective nuclear charge is the influence that the nucleus has on the electrons via Coulomb's law. So here's what that means. Remember, your nucleus is made up of your protons and your neutrons. Your neutrons have no charge, your protons are positive. Electrons are negative. So your positives are going to have a pull on the negatives in the electrons. So the more positive you have in your nucleus compared to the electrons in your energy levels, the greater effect it's going to have on those electrons. And a lot of this has to do with distance as well. So when we talk about periodic trends, we're going to use this to explain why things with a greater positive nucleus require more energy to remove those electrons. Okay, what are we going to talk about next? Shells, subshells, and orbitals. So again, these are terminologies. Shells are your energy levels. So we, up until now, pretty much referred to them just as energy levels. But you'll also see referred to them as shells. They get numbered 1 to 7. 7 is the max. 1 is the lowest. We don't have a 0. I guess technically that would be the nucleus, but that, yeah. So they're numbers 1 through 7. They also correlate to your rows on your periodic table. So that the row on the periodic table that the element is in, with the exceptions of the D blocks, those are the highest occupied energy levels. So if something is in the 3rd row on the periodic table, you know that those elements have electrons in the 1st, 2nd, and 3rd shell. They do not have electrons in the 4th, 5th, 6th, and 7th, at least in their ground state. Their subshells are also called sublevels. So those are the letters that we refer to on the periodic table. So those are the blocks. So the S, P, D, and F block. So your S block are the first 2 columns. Your P block are the chunk on the right side of the periodic table. So those are primarily your nonmetals and your noble gases in your metalloids. Your D block are the transition metals in the middle. And your F block are the lanthanoids and actinoids down at the bottom. So we can use these to kind of tell where the electrons are. The shells and subshells together help tell you the location of the electrons. Yes, that's what I wanted to say. Okay, now here's the last part, which are orbitals, and this gives you the shape. Okay, so different subshells have different shapes. So the S subshells all look like spheres. The P subshells all look kind of like little dumbbells, little balloons. And then they get more complicated as they go on. You don't have to be familiar with the shapes in AP Chem. I just want you to understand that the orbitals tell you specific locations, specific areas of probability where an electron is likely to be. So it's not just in that energy level. It's not just in that energy level in that subshell. It goes even farther in that energy level into the subshell, into these specific regions where an electron is likely to be. But we're not going to get that complicated in this class, but that's something that will come in your chemistry future. Okay, so if we think back to the original objective statement with this topic, we need to be able to write electron configurations governed by the off-bow principle. The off-bow principle says that the electrons are added individually, one at a time, from the inside out. Okay, so I have this diagram over here on the right. This is something that you will either want to have this diagram memorized or just practice with it, and then you can use your periodic table, because let's be real, we don't need one more thing to memorize. But you're always going to fill from the inside out, and so they go in a specific order, and it follows, conveniently enough, the order on your periodic table. So you're always going to start with 1s, and you fill in 2 electrons there. Then you go to the 2s, and you get 2 electrons in the 2s. 2p, you get 1 electron. So if you look closely at this diagram, there's 3 little dashes there. When the electrons go in individually, they go in single first. Okay, so you get 1 electron in each of those little spots, and then you'd go back and you'd pair them up. Okay, so if you put 4 electrons into the 2p, you actually have 1 pair and then 2 singles, because they go in individually and then they pair up. That goes back to Coulombs Law. So electrons, remember, have the same charge. Like charges repel, they don't want to be next to each other. So if they have the space to spread out, they're going to spread out first, and then they'll partner up. Electrons are willing to partner up with one other electron, but that's it. That's when they reach their limit. And so then it keeps going on and on into the 3s, 3p, 4s. Don't forget, we did this when we did electron configurations. In your first chemistry class, it goes from 4s back down to 3d and then back up to 4p. Remember, the d drops in energy level. And then the F block is going to drop 2 in energy level once you reach those. Otherwise, it pretty much goes in order. Couple of things that I want to make a note of before we wrap up this topic. There are some terminology. There's certain types of questions that you're going to be asked about this. So not only are you going to have to be able to write the electron configurations of neutral, just regular atoms, you're also going to need to be able to write electron configurations of ions. I find this easiest to do by writing the normal electron configuration and then either adding if it's a negatively charged ion or subtracting if it's a positively charged ion, however many electrons you need to add or remove. Don't forget that they go into the, that they go in or out of the highest energy level. So for example, when you're working with electrons around here in this 4F, 4S, 3D, 4P area, 4s and 4p are higher in energy than the 3d. Okay, so if you have something whose electron configuration ends in the 3d, when you gain and lose electrons, you're actually going to gain and lose them out of the 4s, because you're going to gain and lose them out of the highest energy level, not necessarily what you wrote last on your electron configuration. The last piece that's going to come up with electron configurations is the phrase isoelectronic. Okay, so if we break that word down, iso meaning the same, electronic meaning, in this case, electrons, things that are isoelectronic are going to have the same electron configuration. Okay, so something that has a positive 2 charge can have the same electron configuration as a neutral atom. So if two things have the same electron configuration, they're considered isoelectronic. So that's something that when you see that word, that's what you're comparing. Do they have the same electron configuration? So that wraps up our topic 1.5.